move on to our second to last presenter, Gabriel LaFrance Fergesen, who was mentored by Marzi Jafari-Atzani. Would you like to introduce Gabriel?
Hello, everyone. I'm Marzia. I'm a researcher at HIPAC Caltech working on observational astronomy, and it's my great pleasure to introduce Gabe, who is a very passionate, motivated, and energetic student. He has so much actually energy that after each session with him, my energy felt doubled as well. And if I had to pick just one outstanding quality about Gabe, it would be his curious approach to every subject and the insightful, detailed question he asks, some of which I didn't know the answer to them myself as well, definitely. And that reminds me of a quote that my PhD advisor was always telling me, that the path to do the good science is start by asking the right and good question. So I think Gabe is on a great path to do science in his future. And okay, with now, Gabe is going to tell us about the project he worked on over the past 2 months. And I can tell you that it was a challenging project with lots of coding and observational astronomy techniques he needed to learn about. And I hope he enjoyed it. Okay, you can start, Gabe.
Okay, let's see. Should I screen share?
Yes, go ahead.
Okay, wonderful. Give me a moment. One moment, please. All right, notepad check. Everyone see my presentation?
Yes.
Wonderful. Hello, everyone. I'm Gabriel LaFrance Fergesen. In my time working with Dr. Marzia Jafari-Atzani, I've had the honor of working to sort galaxies with machine learning to try to find a low-cost way of finding anomalies in these massive multi-wavelength astronomy catalogs. But first, a bit about me. I'm a freshman at Pepperdine. I'm majoring in physics and mathematics, and I'm also getting a minor in literature. I've always loved science. I've had the opportunity to be part of a Caltech bioengineering team, and also the primary programmer for a first robotics team, specializing in artificial intelligence, which I loved. And also, when I'm not doing research, you can find me surfing and hiking. There's a bit of introduction we have to get through, but bear with me. We're going to learn about the fundamentals of multi-wavelength astronomy. We're going to get beyond visible light and learn how to discuss the world in colors you can't see. We're going to learn a tiny bit about the Hubble Deep Field and how that led to the dataset I studied, the Cosmological Evolution Survey, also known as COSMOS. Imagine a flame. Now, we all know that when flames become hotter, they become bluer. And here's the thing. If you kept making that flame hotter, I don't know how you would do it on a stove, but if we kept making that flame hotter, it would stop emitting invisible light altogether. As you kept turning it up, it would start emitting an ultraviolet. Then it would start throwing off X-rays, then start throwing off gamma rays. And simultaneously, if we cooled it down, like perhaps by turning it off, it would stop emitting invisible light as well and go to infrared, and then to radio, and then longer and longer radio waves. Obviously, there is more being emitted than just visible light, so we have to learn to study the universe this way as well. Which is why we have to think about the world through filters. We can't actually see these colors. Our eyes aren't made to see them. So in astronomy, we work by creating filters that react to a certain band, a certain range of length in the electromagnetic spectrum, and then react. And then we create what are called colors by subtracting the values of two of these filters. It's not very literal, but it is a way of understanding these things. It's a form of data we can get. Now, the Hubble Deep Field. The Hubble Deep Field is fascinating to me, and also it's key to this project, because when the Hubble Deep Field project was started, there were papers published that the Hubble telescope would find nothing. It was created by taking an extremely long exposure of an area of the sky that was not thought to contain that many stars. Instead, they found objects dating back to what astronomers believe to be the Big Bang, or seconds before it. And that led to the Cosmos 2020 survey, where 6 telescopes from around the world, some ground-based, some space-based, scanned an area of the sky in incredible detail that was a bit less than the size of a penny. To understand modern astronomy, you also need to understand spectral energy distributions. Because we're looking at more than just visible light, to understand any given object, we're trying to find out how it emits over a range of the electromagnetic spectrum and the magnitude of that emission. And that gives us tons of data points. There's a process called SED fitting that tells us quite a bit, where we take those data points and try to extrapolate out the full line, the full understanding of how that star or galaxy or whatever else is emitting, and then actually try to fit another one of those lines, another spectral energy distribution over it, so that we can understand what type of object it is, because if it fits another spectral energy distribution, we know that whatever object created the data is effectively the same as the other. Unfortunately, this is computationally very difficult. Unfortunately, this is my computer setup that I had access to during my project. So we needed something simpler to access this data. With 966,000 objects, it's difficult to know where to start looking through one of these modern catalogs like Cosmos 2020. But in science, we're always looking for non-standard objects, something that deviates from the norm so that we can learn something new. And we could find that by fitting SEDs of known objects to everything in the 966,000 objects observed by every one of those 6 telescopes. That would take forever. I don't have the computer power to do it. So more recently, artificial intelligence has managed to create incredible insights using very, very fundamentally simple data, finding patterns that were overlooked by other systems. So perhaps we could do something similar to understand these. Now we return to colors. Because instead of using SEDs, instead of using curves, this project entirely relied on colors. We defined 10 different colors using, I believe, 19 different filters from the telescopes. And by creating a comparison of the magnitude seen in each of the filters, we created a data point describing each of these galaxies. So with these 10 data points, we then fed that into a basic classification system. We being I had some assistance with programming, which was wonderful. So the pipeline for the data was, we restricted the data that, I restricted the data that entered the model to be only that which was observed by every one of the telescopes, so that way we avoided incomplete data. Then from there, we restricted the redshift range visible in the training data, so that way we were looking at very, very close objects, astronomically speaking. We then converted everything to the right units, which produced quite a bit of bad data, which was subsequently deleted automatically. That reduced the amount of data we had to deal with even more. We then ranked the outliers using the local outlier finding classification method, where you compare every point of data to every other point of data, looking for clusters and looking for the number of neighbors to see how much each data point deviates from the overall structured information you have. And then from there, I explored the data of those outliers. So one of the attributes I investigated was star formation rate. In this histogram, blue shows all of the data that was fed into the model, all 10,286 objects, and the red shows the top 500 outliers. As you can see, there's a strong leftward shift in the histogram for the outliers, showing that the star formation rate in them is significantly lower. And additionally, if you look at the range from -8 to -4, you can see that far higher percent of the outliers covered far lower objects with far lower star formation rate. Specific star formation rate makes this even clearer, but also gives us a picture of the mass of these galaxies. Here, blue is all the training data, red is the top 1% of outliers from that data, and you can see that we have a large number of objects that have low star formation rate and are also quite heavy. This is a UVJ diagram. They're typically used to classify what type of galaxy you're looking at by comparing the U minus V filter and the B minus J filter. Here we have it separated into regions, the bottom being star forming. The blue shows all of the training data. The red shows the top 1% of outliers again. And I'm certain it's very evident that the outliers are highly concentrated in the dusty star-forming galaxies and the quiescent galaxy area. So the outlier system is indeed picking up on galaxies that are indeed outside of the range of what would be expected, these dusty and quiescent galaxies. Quiescent, sorry. Although I'm certain everyone can notice that the model was unable to discriminate between quiescent and dusty star formation galaxies. A caveat to this whole technique, to this whole process, was that our input was 10 colors. 7 of those were raw data. 3 were processed data from, yes, fitting an SED. So we mainly fit an SED to the data so that we could get the redshift, so that way we could do so that we could take what's called a rest frame, meaning that we shifted all the data to having no effect really from the redshift. Without this rest framed data, the model was completely unable to draw any sort of inference as to what data deviated significantly from all of the others. We needed at least one of these rest framed data types, we need at least one of these colors to identify the outliers. And so all the others really serve to fine tune the model. The next steps of this project are definitely getting the dusty / quiescent classification much better. We could try rest framing all data, considering that it had such a significant effect. And we could also try applying another machine learning technique to this data. I wrote a significant amount of this project's code. In the course of this project, the final code is 467 lines. I would like to acknowledge Marisa Jafari-Yazani for assisting this project in every way conceivable and supporting me through late night debugging sessions, and 3 staff, especially Dr. Ariana Arista, for organizing this incredible program, selecting so many excellent speakers, and giving high school students a connection to NASA. It truly is incredible. And I'd like to also thank my mother for introducing me to science and to N3. I love you so much more deeply than you will ever know. I hope she's in here somewhere. Thank you.
Thanks, Gabe. You have me choking up with that last acknowledgement. How sweet. Great work.
Wow, Gabe, that was great. Sounds like you really did a lot of work and learned a bunch of stuff that will come in handy in your future.